All right, let's go and get started. I'm going to go ahead and get the sign-in sheet passed around. All right, so I've got a couple announcements for you. So you've got that homework design, or the design attention members homework that's due on Monday. I have homework 2, but that's actually homework 3. Has everybody started homework 3, or at least given it a once-over? I will say this, that's the one homework you probably don't want to put off until the last minute. If you take it a little bit at a time, it'll be all right. But if it's Sunday at 11 p.m. and you go, oh, there's that steel homework due tomorrow morning, it's going to be a late night. So I would just take that sort of one step at a time. I've got homework 2 graded. I've been sort of here and there passing that out. Let's see, did anybody not get theirs? Okay, all right, let's see. Mr. Fadiga. Let's see. Miss Clark. Okay. All right, okay. So Miss Davis, now I got yours. Let's see. Did I get you yours?
Yeah.
Okay. Let's see, am I missing? Mr. McCracken, there we go. That's what I'm missing. All right, let me go ahead and get a solution passed out for this. I got to be honest, there's really not a lot really to say about homework 2 because you all did pretty well. The only thing that I guess is worth mentioning is that just making sure you're checking all your failure paths for net area, make sure you're checking all your cases for shear lag and whatnot. But by and large, everything was pretty straightforward. So I'll just walk through the solution real quick. So here's problem 1. I think the problem was pretty easy. And as you went through and started checking net paths, you probably found that there was a pattern. More holes ended up yielding less net area. So the one that governed was that really long one. What was it, like C, D, E, F, H, I, L? So that's the one that ended up governing. Got a net area of about, I think it was like 5.9, 5.93. Okay. The angle and the channel. For the angle, you had to make sure you were checking case 2 and case 8 associated with shear lag. For the channel, it was just case 2 because it wasn't an I shape and it wasn't an angle, so you didn't need to worry about any other cases of shear lag. But you had a number of cases with stagger. So for instance, looking at the channel, so here's the channel. Remember, you've got to check all of the associated paths along the lead line. So for this, you've really got 3 potential paths. You've got path 1 that sort of just directly cuts like that. You've got path 2 that can sort of do this. Remember, it can be symmetric. You can flip it up and down. That's fine. And then path 3 will sort of go like that, go down, and then go down like that. So you've got 3 potential failure paths. The third one was the one that ended up governing, but you got to make sure you're checking all of them. But other than that, I don't really think there's really a whole lot to say. I think you all did very well. If you came in a little late, no big deal. I'll just get you. I've got a pack of them up here. I'll just pass them out near the end. So I'm going to go ahead and pass these out. Let's see. 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look. 2, 3, 4, 6, 7, 8, 9. I'm just going to start that over there. Mr. Lewis. All right. Does anybody have any questions about this or about homework 3? I've already had a couple questions about it. Does anybody got any others? All right. Okay, so a couple other announcements. So let's see. So I wanted to mention the steel bridge because the steel arrived in the engineering labs over here. It was Monday. So they're going to be working on this real soon. They're going to do a lot of cutting, a lot of grinding, a lot of drilling, a lot of welding. So if you're interested in getting involved with that and getting your hands dirty, I'd contact Austin Page. He's the steel bridge captain this year. His email is page44 at marshall.edu. It's a lot of fun. If you're interested in steel and interested in getting your hands dirty, this is definitely a worthwhile endeavor. Also, again, I'm I'm gonna sort of keep this up here. Remember, we got our first celebration of learning next Friday, and we're gonna start a little early again, just to make sure everybody's got time. So Friday the 17th, we'll have our first exam. Everybody good? All right. Okay, so today we're sort of going to get into a brand new topic. I mean, we've spent the last 6 or 7 lectures talking about tension members. So literally taking a piece of steel, yanking on it, and asking ourselves the different ways that it can fail, and ultimately trying to design one, selecting a tension member to resist, certain loads, certain dead loads, live loads, etc. But up until now, we've really sort of put the blinders on in regards to the bolts, to the connection. I mean, we've just, we've been given a design scenario, and here's the connection. Just go to work. Well, now I want to take some time and talk about the connection. Considering what we talked about last time when we discussed the Hyatt Regency collapse, that was a really big deal. A lot of people lost their lives, but one of the details that might have been glossed over a little bit was it wasn't the main member that failed at all. It was the connection. Okay, connections, just by their behavior and by their patterns, they can be kind of difficult to design and design correctly. So I want to go through some of the fundamental basics associated with connections, the different ways that they can fail, the associated limit states, layout requirements, and things like that. And we'll have a few examples and ultimately get into some design. Okay, so let's sort of get into this. I'm going to start off and let's just talk a little bit about bolts in general. Bolts are a little unlike some of the steel grades that we use in terms of availability. I mean, there are some unique little differences here and there between bolt grades, but by and large, there's really only 2 grades or 2 types of bolts that we're going to use for most civil engineering structures. We're either going to use A325 bolts or A490 bolts. And if you just have a structural bolt and you look on the head, you'll be able to tell what it is. So for instance, I've got A490, you can tell what the grade is. The first symbol will tell you the grade. This symbol down here, this LE, that's a reference to the manufacturer. So that particular bolt was manufactured by Lejeune. That's their manufacturer symbol. And we have, Nucor, Yamato, and all sorts of other bolt manufacturers, and that's how they indicate that. Difference between A325 and A490 is A490s are a little more expensive, but they're a little stronger. So it's a trade-off, and it just depends on the prices when you're working on your project. I mean, is it cheaper to use, let's say, 10 A325 bolts or 490s? Well, it just depends on the price. And you know as well as I do that steel prices tend to go up and down, so it's one of those things, just sort of depends on what day of the week it is. Now, I'd be remiss if I didn't at least mention A307 bolts. They're listed in the spec, but they're really not very common. They're mostly used for a temporary erection. If you're lifting a member, maybe just take an A307 and hold it in place so you can let the crane off and then go through and fasten your connection with either A325s or A490s. So they're there, but they're really not used very common. Sound good? All right. Now later on, we're going to talk about the different types of installation methods that you can use for installing bolts, and it leads into 2 different classes of bolted connections that we'll design. We either design bearing type connections or slip critical connections. And the difference is that when we use slip critical connections, we're actually counting on that friction that you develop between the 2 plates. And that's really important in 2 big scenarios. Number 1, when you're looking at a bridge, because you always use slip critical connections for bridges. And 2, during earthquake design, because you always want slip critical connections for earthquakes. And they tend to have a lot of demand on them. Because of the nature of slip critical connections, there's a lot of proprietary items out there. A lot of folks are selling, special wrenches and special type of bolts that are that'll help you install slip critical connections safely. Like, hey, you'll save a lot of time, but by the way, buy our wrench that costs X number of thousands of dollars. So you can install these. Because of that development, because of the the different little intricacies here and there with different bolts, there's a number of different ASTM grades that all kind of mean the same thing. They kind of either reference to A325 or A490, but they actually have different names. So the way that the steel manual resolved that is they just said, all right, let's just keep it simple. We've either got Group A bolts or we've got Group B bolts, okay? So Group A bolts would really reference all these that all have the same material properties and whatnot, but they just fit a different spec because they're manufactured a little bit differently and they're installed a little bit differently. So I guess the reason why I'm mentioning all of this is that when you open up the manual, it's going to list Group A and Group B. But if you're in a fabrication plant and you start asking everybody where's the Group A bolts stored, they're going to look at you a little weird because there's no such thing as Group A bolts. They're either A325 or A490. Does that make sense? Are you okay with that? Okay. Now, I'm not going to, make you, verbatim draw this out on an exam and list all the different, terminology, what's the grip, what's the shank, and all of that. But I do want you to have at least just a general idea of what a bolt looks like. The really, I guess, most important parameter I want you to understand is that for a typical structural bolt, the threads, they don't go all the way from end to end, okay? So, we talked about this last time, but more often than not, when I have a structural bolt, I'm taking that bolt and I'm loading it in shear. I'm taking it and I'm shearing it like this. So one of the big questions you've got to ask is, are you shearing through the threads or are you shearing through the shank? And that matters because where do you think that the bolt is strongest, through the shank or through the threads? Through the shank. So where the shear plane is, where you're actually shearing through, that matters, okay? And we're going to see some notation here in a little bit that'll kind of expand on that for us, but I just wanted you to kind of get that general idea. Now, let me ask you this. If you're looking at detailing a connection, you're doing some calcs, and you don't know whether or not the threads are included in the plane or excluded, are you going to assume it's through the shank or through the threads? Through the threads, absolutely. So when in doubt, always assume that your shear plane's going through the threads. Sound good? All right. Now, I don't want to belabor this too much, but I at least want to make sure that everybody kind of understands what happens when you take plate A and plate B and connect them together with a given bolt, okay? And by and large, what's going to happen is you're going to develop three different potential forces, okay? Number one is shearing through the bolt. You're taking a bolt, it's connecting two plates and you're loading it. You're going to be shearing that bolt. You're going to develop a shear stress within that bolt. So one of the things that we're going to try and prevent when we start doing a lot of our design is let's make sure we don't shear the bolts in half. Simple, right? That's force number one. Force number two is what we call bolt bearing. So the idea is you've got this bolt going through a plate. The bolt literally might come into contact with the plate and start loading or bearing onto that plate. So the plate itself might experience failure. It might want to tear out, or you might want to take that bolt hole and stretch it out a little bit. That's going to be a limit that we try and prevent. The third one, and this is the one that goes into slip critical connections, is friction. Let's go back to basic physics, right? You take a normal plane, you smack a force on it, you develop a frictional force between those two planes, right? Remember that? You got your normal force multiplied by your coefficient of static friction. Remember that? Well, think about what happens when you tighten a bolt together. You got plate A, plate B, you stick a bolt through them and you start tightening. What's happening to the two plates? They're coming together, right? You start cranking on that bolt quite a bit, those plates are really going to get sandwiched together. There's your normal force. You got steel connected with steel. There's a coefficient of static friction. You can get some frictional force developed between those two plates. You can actually rely on that for design purposes, which we do in cases like bridges or cases like earthquakes. And we'll talk about the different ways that you install that and the different ways that you can develop that friction later on. So far, so good? Okay. So these are the different forces that you'll get for a given bolted connection. This can result in a number of different failure modes. Now, so I've got here just something simple. I've got a single bolted joint. I've got a plate lapped onto another plate and just a single bolt through it. Now, right now what I've got is I'm discussing the different ways that that particular connection can fail. Now, some of these you've already seen, right? I mean, like the one in the middle, fracture in the net section. We've already done that, right? Just a, samurai sword or a lightsaber through the plate, net area, shear lag factor of 1. Everybody knows that. Also, gross section yielding, right? Just remember hitting FY in the main body of the member. That's a failure mechanism as well. This is the stuff that we did before when associated with tension members. Same story here, right? But what I want to focus on is the stuff associated with the bolted connection. So one of them, shear failure in the bolt, literally taking the bolt, shearing it in half. That's something we're going to want to prevent, okay? Another one is sort of represented by these two right here. This is what's called a bolt hole ovalization. So the idea is, here's my plate, here's my bolt hole, I've got a bolt going into it, and I'm loading it in shear. So that bolt is coming into contact with that plate, and it's bearing on it quite a bit. That might have the tendency to want to take that bolt hole and just stretch it out, right? Make it longer, elongate it. Well, we really don't want that to happen either, because that could potentially lead to tear out. Actually, that little bit of plate right there, just ripping it out. It's almost like a mini block shear, right? Just taking that little sliver of plate and just ripping it out. Imagine that happen across the entire connection. That's obviously something we wouldn't want to have happen. Make sense? Now, there's a couple other mechanisms, things like tension failure of the bolt. That would be if we're taking a bolt and loading it in tension instead of shear. We'll talk about that a little later. Also, we could have something like bending failure, but by and large, bending failure really isn't going to govern. We're really going to be more concerned with this. And I got an image of that later on. Everybody okay with this so far? Any questions? All right. All right, so I mentioned this before, but we're really going to focus on two different types of connections. I'm going to spend most of my time today and probably going into next time discussing bearing type connections. So this is when I'm not really counting on that friction that's being developed between the two plates. I've literally just got bolt shear and bolt bearing to worry about. Like I said, slip criticals where we count on the friction. Like I said, you can count on the friction, but by and large, when you use slip critical connections, if you really need that friction for the connection, you're probably going to end up using more bolts. And a good rule of thumb is if I need, let's say I need about 10 bolts for a bearing type connection. For that same connection, if I wanted to use slip critical bolts, I'd need about 20. But, I mean, when you need it, you need it. I mean, like I said, in things like bridges or things like earthquakes, we really don't want those bolts loosening during a lot of that, cyclic loading, so we need them to stay there. And in those instances, you just kind of have to go with the slip critical connection. But for right now, I'm going to focus on bolt bearing, and then we'll take care of slip critical later. Sound good? Yes, sir. Yes.
Just that the magnitude isn't enough to be considered.
Exactly. To elaborate on that a little bit, when you have a bearing type connection, essentially all you're worried about is getting the bolts just sort of snug tight. And snug tight is sort of a loose definition, okay, a very loose definition. What's snug tight to you versus snug tight to you or you. And it's loose because we're not worried about developing a certain amount of friction. But for slip critical connection, we really are trying to achieve a certain amount of friction. So this is when you're using, like a glorified torque wrench to get a specific set torque in that bolt and ultimately develop a predictable amount of friction. But in bearing type connections, we're not going to worry about that. Are you going to get some friction? Probably, but nothing that you can count on. I mean, installing a slip critical bolt properly, getting that specific amount of tension, takes time, and ultimately that's going to cost money. So you've got to be really choosy in terms of when you use it. And that's why I mentioned there are specific applications like earthquakes and bridges. Like if we were out in LA, we'd be using slip critical connections all over the place. Does that sound good? Everybody else all right with that? Good. All right. All right, so let's sort of get into the math a little bit. Let's sort of get into to what's going on. So when we talk about bearing type connections, we're really associated or trying to discuss two different failure phenomenon, either failure of the bolt or failure of the plate. So let's talk about the bolt first. Okay. Now, I'd be remiss if I didn't mention that there's other ways that a bolt can fail. You know, you can have a bending failure of the bolt. You know, you're taking the bolt and you're sort of going like that. It is very possible that that bolt could experience, you know, some type of bending. Okay. Now, that is very realistic in a connection where you have just one bolt, okay? But we haven't dealt with that before in this class, and you won't deal with that very much in practice either. I mean, look at the connections that we've been dealing with so far. They've had, what, like 12 bolts, 16 bolts, or 9 bolts, or something like that. Because, you know, if you've got a connection, because there's so many other bolts going on, and because there's such a sort of a constrained geometry, if you've got multiple bolts, A, this really isn't likely to happen, that's point one, and B, this is definitely the more drastic failure. I mean, if your bolt bends, yeah, it sucks, but it's still there. You know, if the bolt fractures, that's a problem, right? Again, going back to my analogy, if this bolt is holding up a bridge that your grandma drives across every day to go get groceries, grandma's in the river, okay, and we don't want that to happen, all right? Sound good? So this is going to be right here our ultimate limit that we're going to check. So let's get into some math. All right, now to compute the capacity, it's pretty simple, okay? All you take is the area of the bolt, you know, pi r squared or pi d squared over 4, and multiply that times a limiting stress, all right? So you look up that limiting stress based off of your grade of your bolt and a couple other parameters that we'll discuss here in a little bit to compute your nominal capacity. Now remember, that's nominal. We have to always at the end adjust with phi. So our phi value for bolt shear is 0.75. And you'll tend to find that pattern across the board for just about everything that we do in this class. If we're talking about yielding, our phi value tends to be around 0.9. But if we're talking about fracture, our phi value tends to be 0.75. Again, you know, if it yields, it sucks, but it's still there. If it fractures, it's, you know, it's popped in half, so that's an issue. So far, so good? Okay. So we've got a couple questions that we need to answer. Number one, are the threads included in the shear plane, and how many shear planes are there? Okay. So let's take them one at a time. Let's start off with threads included in the shear plane. So we mentioned this a little bit ago, but you know, threads included in the shear plane, that matters for capacity. Because again, which bolt do you think is weaker? One on the left or the one on the right? One on the left, exactly. Because if I'm shearing through threads, that's less area, right? It's less area, so there's less material to resist that load, okay? So we as engineers, we need to know that. Now, it's very easy to spec a bolt that has threads excluded from the plane. You just have to select the bolt accordingly. Yes, sir? You're exactly, okay, to answer your question, yes, it would be advantageous, but sometimes it's not so simple because it's going to depend not only on the availability of the bolt. You know, let's say, you know, I choose a 3/4 inch diameter bolt. Well, 3/4 inch diameter bolts are available in various lengths. So I might get a 2-inch long bolt, a 3-inch long bolt. So that's one parameter. Another parameter is the thickness. You know, is this 5/8 inches thick? Is it 3/4? Is this a 1/2 inch? So can you spec it? Yeah, but not all the time. You know, you can't really spec it all the time. And really, in general, you kind of just need to be able to assess both. Fortunately, I'll say it's easy to assess both. And again, going back to my original point, when in doubt, threads included or threads excluded? Included, all right? So when in doubt, if you don't know, assume threads included. When I'm in design mode, I always assume threads are included. And then what I would do is I'd go to the catalog and I'd say, all right, now it's time to start buying bolts. And if I find, hey, I can buy a bolt and the threads are excluded, I'll go back and change my design. I'll see if I can cut off a few bolts. That make sense? Does that answer your question? Everybody else good with that? That's a good point. Okay. So, all right. So threads included versus threads excluded, this is how we handle this in the manual, okay? So first off, I want everybody to go to this table in the manual. So first off, this should be familiar because we looked at this table last time, okay? So I'm on 16.1, so I'm back here in the spec, and I'm on page 120, okay? So let's see. It should be on the left page. It should look something about like this. Everybody find that? Okay, all right. Now, so this is the table that lists our nominal shear stress capacities as a function of our bolt grade. So let's look at the two Group A rows. And you can read it out. You say, the first one says what? Group A bolts when the threads are not excluded from the shear plane. And then Group A bolts where the threads are excluded from the shear plane. Everybody see that? Now, look at your shear stresses. What's the shear stress for threads included versus threads excluded? What we got? 54 and what? All right, everybody's with me. So this is how the manual accounts for that. It just reports a different shear stress value. So if the threads are included, we have a weaker bolt and then ultimately a smaller FNV. All right? Does that make sense? So it's a pretty easy way to realize that. And another thing that we engineers adopt for a naming convention is we just use what you see down here. So for instance, if I ever say Group A in bolts, I'm talking about Group A bolts where the threads are included. If I say Group A X bolts, I'm saying Group A bolts where the threads are excluded. Okay? So Group AX bolts are the ones that are stronger. It's pretty creative, right? You like that? All right. Everybody good so far? Yes, sir.
Usually, would your tensile strength on your plate not govern over the bolt strength? Because like A490 bolt would obviously be a lot stronger, but you're going to design for the strength of the plate, not the bolt.
Well, I'll say this. You're sort of, in a roundabout way, opening up a can of worms because there's two different ways of going about this. One way to design a connection is to design for the loads. We're not designing for the plate. We're saying, okay, we have a dead load of 50 kips and a live load of 80 kips. Pick the number of bolts for those loads. That's one philosophy of connection design. The other is design the connection so that it doesn't fail, that the plate fails. That's a whole nother can of worms. Okay? But let me say this. If you give me a connection and you say, well, isn't the bolt going to fail before the plate does? My answer is, I don't know. I have to go through and do the math and see. So before we said, okay, now we can compute gross section yielding, we can do net section fracture, block shear rupture. All that stuff is still relevant, but now we're looking at, okay, what about bolt shear? What about bolt bearing? What about all that? It's possible that the bolts govern. It's possible they don't. There's no simple yes or no. You just have to go through and check them all. So, is everybody else all right with that? This is important, okay? All that stuff that we did before, it's still relevant. We're just, for now, focusing on the bolt shear and the bolt bearing. So that is important. Everybody good? Okay. Now, so whether or not the threads are included or excluded is important. Here's another thing that's also important, and that's whether or not we're dealing with a situation of single shear or a situation of double shear. Okay? Now, if we're dealing with double shear, look what's going on. This would be something like a splice connection. So, for instance, if I've got member A and member B in some structure and I want to splice them together, I might have a plate behind it and a plate in front of it and a bunch of bolts going through each end. So if I look at each one of those bolts, there's not one plane that's being sheared through, there's two. Does everybody see that? Now, what ends up happening is this. This bolt down here is twice as strong as this one right here. Now, I'm not saying that the bolt magically got twice as strong. I'm not saying that. What I'm saying is that I've got to shear through more bolt to fail this one than that one. I've got two areas that I've got to shear through. So again, it's not like the bolt got stronger. It's just there's more material to get through to snap that bolt, not in half, I guess, snap it in three pieces. Does that make sense? Everybody okay with that? Okay. Now, you start thinking about this. Well, we've got threads included, threads excluded. We got single shear and double shear. I start thinking, well, I like Microsoft Excel. Maybe I can write a little spreadsheet that does all this math for me. Well, the folks who wrote the manual thought the same thing. So I want you all to turn to a section here in the middle. This is one of our first design aids. I want to spend a little bit of time playing around with this. So to find it, okay, remember those black and gold tabs right here? If you look, there's literally a tab that says bolts, okay? So that is part 7 of the manual. In part 7, I want you to turn to page 22, okay? And you should see this on the left, table 7-1, available shear strength of bolts. Everybody find that? Okay. All right. First off, my little star, my little outline, remember this is going to be a guide that we use quite a bit, so you're probably going to want to put a tab there, or I see some folks already breaking out the sticky notes. That's a good one to tab, okay? So that's point 1. All right. Point 2, I mentioned this earlier, but I'm going to elaborate on this. For us, we're going to use the blue numbers, not the green numbers, or the ones that aren't shaded. Because for us, we're not using allowable strength design, we're using LRFD. So anytime that you open one of these guides and there's green numbers and blue numbers, we're going off the blue ones, okay? Sound good? All right. Bless you. Now you start going through this guide, I think you're going to find it's really simple. Okay, this is really simple. Let's just sort of play around with it a little bit. I'm going to come up with a quick example. So let's see. Let's say we've got group A, we'll say X bolts. We'll say the diameter of the bolt is, I don't know, 7/8 of an inch. And we'll say it's in double shear. Let's see how strong that particular bolt is. Well, let's see. I'm on ASTM designation. I've got Group A and Group B, so I'm looking at Group A. We've got threads excluded, so I'm on this little row down here, right? And we're in what? Single shear or double shear. We're in double shear. Everybody see that? So Group A excluded double shear, we're looking at what? This row, yeah, exactly. You got to have me. That row right there, we're looking at 7/8 inch diameter bolts, so right there, 61.3. Simple, right? So instead of doing pi d squared over 4, looking up the FNV and multiplying by phi, it's right there. So that is a very nifty guide that you're going to want to tab if you haven't already done so. Like I said, I saw a couple people breaking out the tabs already, so you're prepared. I like that. All right. Everybody okay with this? Yes, sir. That's a good question, and the answer is it's possible. I was doing some research on a bridge in Jackson County, West Virginia. It was near Ripley, and we were looking at this particular connection where there were these 2 through trusses, and then there were floor beams framing into the through trusses. So you had, gusset plates and members, but then you also had a floor beam with an end connection plate. So if you looked at those bolts, yeah, they were in triple shear. Okay. Now to go to your multiply by 2, I mean, look at each row. Like look here, we got 17.9 and 35.8. The difference is they just multiplied by 2. So if you had triple shear, just take that and multiply it by 3. It's possible. I'll go ahead and it's not very common, but it happens. So that's a good question. That's good. All right. So each one of these values that you're looking up are kips. Okay. So we got 61.3. That would be 61.3 kips per bolt. Okay. So what I would then do is I'd say, well, how many bolts are in the connection? If there's 6 bolts, take that number, multiply it by 6, and there's the bolt shear capacity for that connection. Now, all that will tell you is how much load it will take to fail the bolts. Okay. The next thing we got to answer is how much load it will take to fail the plate, okay? Because those bolts are coming into contact with that plate, and that still matters too, all right? Make sense? Okay, all right. Very good. All right, now let's talk a little bit about the plate, Okay, so I've got here a connection that was loaded in shear, and they took the bolts out and they sort of took a picture of it to give you kind of an idea of what's going on. And ultimately what can happen is one of two particular phenomena. So the one on the bottom is the one I was mentioning earlier when the bolt hole kind of wants to stretch out a little bit, wants to ovalize, if you will. So, they took this plate, they loaded it in shear, so, here were the bolts, and they took the plate and they yanked it up, so the bolt suddenly came into contact with the plate, right? Now, like I said, one of two things can happen. See right here, it's sort of, the bolt kind of mashed into the plate, and the plate almost turned into like a little bit of Play-Doh right there, and it sort of, experienced that permanent yielding. This phenomenon right here, we call that ovalization. It just sort of mashes in and stretches out the hole a little bit. Now that's one particular way that the plate can fail. Another is tear out. It's a little hard to see, but maybe I'm going to color it in a little bit. But on this one up top, you can kind of see it like right there and about like right there. Does everybody see that? What's happening is the plate is actually starting to fracture along those paths. Now, let me ask you a question. What type of force do you think those paths are seeing? The tension, shear. There you go. Now, here's another question. Remember when we talked about block shear rupture and we got into von Mises? Remember I said there's this number that's going to pop up? This particular number. Anybody remember what that number is? When we did the block shear path, all the numbers that were associated with shear had a particular multiplier. It was point something. Not 0.75, a little lower. 0.6. There, 0.6. Let me go back to, you're like, up and down. No, hold on. I want to go back to that real quick. So, remember this? Remember this right here? The 0.6 associated with that? Worked out pretty well. Y'all remember that? Remember, anything that's associated with shear in the manual is going to have that 0.6 built in there somewhere. The bolts have the 0.6 built in as well, but there's a lot of background additional manufacturing parameters that go into the background. That's why they just say 54 for threads included and 68 for threads excluded. But it's in there. It's in the background. All right. Where was I? All right. Everybody okay with this so far? Okay. All right. Now, let's talk about the math. So, to determine the capacity of a bolt-in bearing, we have the following expression. Now, it's a little weird the way it's written because you've got Rn equals a pile of junk such that it's less than or equal to another pile of junk. Remember that? Anytime that the manual expresses that, it's just the manual's way of saying it's the minimum of those two values. So I'll take this equation and reformat it a little bit to result in a little less number crunching on the calculator because I'm lazy, and if I can calculate the capacity and less button crunches on the calculator, I'm going to do it. Okay, so we've got Rn equals these two quantities. Some of these should be pretty familiar. Some of them are going to be new. So, for instance, T, that's the plate thickness. That's easy, just whatever the thickness is. If it's a flange thickness or a weld thickness or a web thickness, you got to look that up in the front matter of the manual. All right. D sub B, that's your bolt diameter. So that's just the bolt diameter for your given connection. And F sub U, that's the tensile stress. So that's easy. I'll tell you right now, the one that's going to give you the most headache is this one right here, this L sub C. Now, L sub C is the clear distance between the material for the given bolts. Okay? Everybody okay with this so far? Let's talk about a little bit about this equation, see if we can simplify it out a little bit. Okay. So remember, anytime you have a pile of junk that's less than or equal to another pile of junk, that's just the minimum of those two quantities. So another way of writing that is it's either the minimum of 1.2 LCTFU or this one, 2.4 DTFU. Now, in terms of behavior, it's pretty simple. This top expression right here, this is the one that's working to compute the bolt tear out capacity. The one on the bottom, or the one over here, or the one on the bottom, That's the one that's trying to predict how much the bolt hole is going to stretch or how much we're going to, plastification we're going to get right around that bolt. Remember how it sort of mashed up and turned into Play-Doh? That's what's going on right here. This one up top, that's for tear out. So far, so good? All right. Okay. Now, let's talk about this LC a little bit. So I've got here just a single plate. I've got 2 bolts in it, and I'm going to introduce some terminology for you. Now, one of these, I say introduce, but you've seen this before. That's S, okay? So S is the longitudinal spacing along the connection. Remember, if we were talking about transverse spacing, we'd call that G, right? Remember, because that's how we got our stagger factors earlier. All right, so this is our center-to-center bolt spacing, and this right here is the edge distance, how far the center of that bolt is from the edge. So think, those are the dimensions that I would need if I was going to start drilling that plate, right? I'd measure that out, and then that's where I would drill. Sound good? Okay. Now that's just the general spacing of the connection. LC is the clear distance from edge of plate to edge of plate. Okay? So by its very nature, we're going to have 2 LC values that we need to compute. Okay? We're going to have an LC for all the bolts that are on the edge, and then an LC for all of the interior bolts. Okay? So let's just take them one at a time. So if I was talking about an edge bolt, and I'll sort of clarify that here in a little bit. So if I'm talking about an edge bolt, here's L sub E. If I want this dimension right there, what do? I take L sub E, and I take off what? Half a hole diameter, right? Or a radius, if you will. So L sub C on the edge bolts is the edge distance minus half a hole diameter. So far, so good? All right, now that's for the edge bolts. For the interior bolts, so here's bolt spacing, and then what I'm going to do, I'm going to take out half a diameter, another half a diameter, so I take off one whole one, right? So here's LCI, the clear distance for an interior bolt, spacing minus hole diameter. Sound good? Now, while I'm at it, let me just go ahead and draw another connection to just sort of clarify some things, because I want you all to help me out with identifying this. All right, so let's say I've got a connection and I'm yanking on this. Okay? So let's draw out some bolts. Let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right, so let's say I've got this. So our edge bolts are the ones that are essentially going to be located towards the back end of the plate. In other words, I'm talking about the ones that are all the way back here. The interior bolts I'm talking about are these, and these. Now I'm calling them interior bolts because look at it like this. Would you agree that this distance, this line right here, that's the clear distance I'm after, right? That's the LCI. Well, that's going to be the same distance for this bolt as it is for this one, right? And for this one. And for this one, right? Assuming everything's evenly spaced, right? So real quick, let's just make sure we're clear on this. How many interior bolts does this connection have? 9. And how many edge bolts? 3. Okay? So everybody okay with that? All right, we're going to do an example here in a little bit, and that'll actually matter when we look at bolt bearing. Yes, sir. What about when you have a staggered connection? That's a good question. The answer is you just have to be a little clearer on your bookkeeping. So I'll do a simple one just to kind of explain. If I had a staggered connection and it was somewhat complicated, I'd probably just make sure I was taking each bolt one at a time and getting the right LC for each one. So, for instance, if I've got this, and I've got, let's say, 1, 2, 3, 4, 5, right? So let's say, so for these 2 on the bottom, my LC would sort of be that distance right there, and the same one for this one, so I'd sort of maybe treat those 2 bolts as the same. And then the center one, my LC is going to be whatever that distance is right there, and then these 2 up here, I'm going to have another one, and maybe something like that, and something like that. it doesn't become technically more challenging. It just becomes a bookkeeping issue. All right? Don't worry, I'm not going to do that on a celebration, because if you can do a grid-like pattern, you can do this. It's literally just a bookkeeping issue. All right. Everybody else okay with this? We good? Awesome. All right. All right, so I want to make some observations about this bolt bearing. Remember this whole 0.6 thing I was telling you about? This bolt tear out calculation that we're doing, remember where we had the connection and we had, sort of that shear failure right here and that shear failure right there? That is essentially a mini block shear check. I mean, think if I was trying to calculate the block shear capacity of that. Now, how would I do that? Well, I'd have the length in shear, right, LC, times the thickness, right, times some limiting stress, times it's in shear, so 0.6, right? So look what I got right here, 0.6, the length, the thickness, and a limiting stress FU. But there's two of them, right? There's a shear path over here and a shear path over there. So this 1.2, I know it's really just 2 times 0.6, and the 0.6 comes from the shear failure, right? All right, everybody okay with this? So I really wanted you to see where this came from. This equation, this top one, it's not magic, okay? It's really just a block shear check on each individual bolt. Everybody okay? Now, I will be honest with you. The second one, this is a little bit of magic. This 2.4 DTFU, the mechanics associated with that ovalization, it's not easy, okay? It's really not easy, because you've got to understand plastic, stress distributions around a circular region. That math gets tough, okay? So this is what we do. We go down to the lab, and we like breaking things, right? Any day with controlled demolition is a good day. So we go, and we go to somewhere like Huntington Steel, and we order a couple hundred different connections. We start varying, bolt diameter and thickness and steel grade, and we start failing all of them. And then we record the stress, and we say, all right, can we match an equation that's simple and that works? And that's what you get down below. So that's an empirical relationship, okay? Again, it results from doing a lot of breaking things in the lab, but that's essentially the long and short of it. All right. Everybody good? Okay. All right. Now here's where you're not going to like me very much. You're not going to be happy with me on this one. So before we're going to, tomorrow, or not tomorrow, on Friday, we'll talk about bolt layout connections, but I got one final, I guess, parameter to run by you that you're not going to like. So when we calculated net area before, when we were looking at tension members, okay, we said, all right, when we calculate a hole diameter, we take a bolt diameter and we add 1/8 of an inch, right? Now, why did we add 1/8 of an inch? Well, we didn't really add 1/8 of an inch. We added a 1/16 twice. We did it for two different reasons. Now, we added 1/16 because we actually physically drilled the hole larger, right? If you got a 1/2 inch diameter bolt and you want to install that in a structure, you have to drill the hole a little bit larger. And for standard holes, that's a 1/16 of an inch. But then we also added another 1/16 of an inch. And we said the reason for that was damaged material. But the expanded reason, expanding that out, is we were trying to ask the question, well, can we really count on that little bit of material right there around the bolt with all the burrs and the damage from the drilling process and whatnot? Can we really count on that to transmit load to the whole tension member? And we said, not really, okay? So we added 1/8 of an inch when we were doing net area for tension members. We're not talking about tension members right now, though. We're talking about actually assessing the capacity of the plate right there around that bolt hole, okay? So because of that, we are using the physical dimensions of the hole. We're not adding 1/8 of an inch for this. We're adding a 1/16, okay? I guarantee you this is one of those details that is very easy to forget, okay? I know everybody's like, come on, really? Yes?
Why do we count on it in this instance? Just because it's not tension?
No. What we're trying, no.
It's physically there in the tension member too.
But what I'm at, no, going back to what I said earlier, what I'm after is before I was asking, can I count on that material to effectively transfer load to the whole member? When I'm calculating bearing capacity, I'm not calculating the capacity of the whole member. I'm looking at each individual little plate one at a time, okay? So I'm actually assessing the physical dimensions of the whole, going out to the fabricator and actually measuring it, okay? In that instance, it's not 1/8 of an inch, it's a 16th, okay? Does that sort of help clarify that a little bit? I know it's one of those details, you're like, come on, really? This is more stuff I got to remember? Yes. It is what it is. All right. One other thing I did want to do for you is this right here. Remember what I did for block shear? I factored some stuff out. So you notice both of these have a thickness. Both of these have an ultimate tensile stress. And I've got sort of a common 1.2, so if I factor that out, I can calculate the bearing capacity of each individual bolt as 1.2 times the thickness times FU times the minimum of either the clear distance or 2 bolt diameters. And it makes the math a lot easier down the line because, I mean, it'll go a lot quicker. If you had to calculate each one of those one at a time, it just becomes really laborious, and there's not really a lot of benefit to the calculations either. It's a lot easier. All right. Everybody good so far? All right. I think I'm going to call it for today. What we're going to do next time is this. We talked about bolt capacity and bearing capacity, but we actually didn't talk about some really simple stuff, things like laying out the connection. I mean, if I do a bolted connection design and I say, okay, we need 8 bolts for that connection, that's not enough. That's not enough to actually go out and fabricate it. I need to know how to space out those bolts. I need to know how far they can be from the plate edge. So we need to talk next time about bolted connection layout. Spacing requirements, edge distance requirements, because there's issues with that. I mean, if bolts get too close together, you can't tighten them. They start smacking into each other. So you have to have a certain minimum spacing. If they get too far apart, there's a potential you get water seeping in between the connection. And water and steel, they didn't go together very well, right? All right. So next time we're going to go into that, and then we'll get into some sort of full-blown design examples. I'll sort of skip ahead a little bit. I want to take a standard, like a typical bolted connection, and let's go through the math. How much will it take to actually fail that connection? And then if we understand that, we can go into, okay, let's start sizing them. How many bolts do we need? How do we need to space them out and to safely resist loads? All right. That's all I got. Sign-in sheets working its way around. If it hadn't already signed in, go ahead and do so. I also have a few more homework assignments for a couple of you all that straggled in a little bit. So that's all I got. For those of you in concrete, I'll see you in a few minutes. Everybody else, I'll see you on Friday.